Okay, so let's see how to do this using MCMC. So let S denote the set of all 5 of 4 by 4 tables of non-negative integers with the same row and column summations as this table, like what I show you here. Say we want to produce a sample of tables from S that are uniformly distributed. This means the probability equals to 1 over the total number of tables in S for each table in S. However, we don't even know how many tables are there in S. But we know the total number is finite, right? So, the thing is that we can create, like what I said before, we can find a transition matrix P, that is a Markov chain, such that the limiting distribution and the stationary distribution of this Markov chain is a uniform distribution, right? So then we know this P, what's the dimension for P? This P going to be, right, total number of S row by the total number of S column, right? This number row and this number column, but we don't even know what's this total number of tables in S. It's going to be a really big number, but it's a finite, right? This P is going to be a matrix, a huge matrix like this. Okay, it's impossible that you're trying to solve each number in this P, right? But we just want a Markov chain that uniform is the stationary. So we can do in this way. Choose 2 rows and 2 columns at random. The intersection gives a 2 by 2 subtable. So what do I mean by that? Let's say make it smaller. Let's say this is my x1, and what I'm going to do is that first I would randomly choose 2 rows and 2 columns. Say I choose this row and this row just randomly. It's like you choose 2 from 4, right? It's a combination, and I will choose, like, say this 2 columns. Okay, so the intersection is the part, intersection of those part, right? Those part. Right, that's the intersection. That's a 2 by 2 table, 2 by 2 subtable. And we toss a coin, a fair coin. If it comes out ahead, we add this subtable, which means 1, negative 1. So if it's ahead, I will do this. This column, a subtract 1, and this column plus 1. And this is plus 1, and this is subtract 1. Okay, so you can see after I did this, this table will become the new table here. New table will become, this is 83, right? This part, this cell will become 83, and this becomes 18, and this is 55, and this is 13, right? That's the new number in those 2 by 2 table, right? So okay, that's what what happens if I get a head? If I get a tail, I will do this way. Okay, in either way, you can see no matter whether head or tail, you actually never change the row summation or column summation. Right? You see that? Because you subtract one here, but you add one here, so the row summation is not changed, and the column summation is also not changed. Right? No matter whether it's head or tail, right? We always keep the row summation and the column summation. And so if you can do this without violating the constraints, okay? Constraint just means that you cannot any number or no number can be negative, right? It could be 0, but it cannot be negative. So you just check, is there any number negative? No, right? Then we can just accept this, right? We will just accept this. If it's not violating, so then in that way, this is x1, this table is x1. After you do this operation, this is x2. This new table is x2, right? This is how we move on according to Markov chain. If after you do this operation, you got some negative numbers, then okay, you just discard this new table. Your x2 will be just the same as x1. Okay, so it's clearly a Markov chain, right? Your future only depends on your current table, right? So this is what we are actually going to do, and this operation actually gives us a Markov chain, right? Note that this Markov chain probability transition is symmetric. Okay, why is it symmetric? Because you always randomly find 2x2 table, and the two operations like either head or tail, they actually are those 2x2 subtable are symmetric. So this whole Markov chain, what I will do in here, this is whole Markov chain is symmetric Markov chain. Okay, so then we know that the uniform distribution is the stationary distribution of our Markov chain. This is exactly what we want. Okay, so this Markov chain can be shown to be irreducible, and the Ergodic theorem says this works. Okay, so you see, this is how I find this Markov chain. I find this Markov chain not just write down the P matrix, right? Because in fact, there's no way you can write down the P matrix in our case. But because my target distribution is uniform, so as long as I make a Markov chain that is symmetric Markov chain, and then we're done. Because the uniform distribution is the stationary distribution. Okay, so instead of write down the matrix T, I actually describe operations on this 4x4 table, how to move on from one table to another table, and that's a Markov chain. That gives us what we want. Okay, and you can just run this Markov chain. You keep doing this randomly, choose 2 column, 2 row, and doing this thing. You can keep going. You got x1, x2, x3, all the way to x10,000, right? You run it long enough. Let's see, you got, because let's say we want just 1,000. Let's see, we want 1,000 tables uniformly sampled from S. Okay, then how to do that? We can run it long enough, like a x 1,000. Hope it's already 10,000, right? It's already long enough, so we just keep x 10,000 and 11,000. Right? You run it long enough, and you keep the last 1,000 x. Those 1,000 x are actually the 1,000 table, because we assume when you run it long enough, it converts to limiting distribution, right? And the limiting distribution, we already proved that it's the uniform distribution. That's our target distribution. So those x, the last 1,000 steps for the Markov chain are actually the uniformly sampled from our S. That's what we want.